in that statement, okay? Is this is still x minus an x coordinate, this is still y minus a y coordinate, x from the plane minus the fixed x point in space, right there, y from the plane minus a y coordinate from that point in space. Is this still z minus a z coordinate?
Yes.
Yes, the only thing we've had to do is we've had to make sure that we're using the z coordinate from the equation of the plane to represent z minus that z coordinate in space. So that's how you create your two variable function in this case, as a measure of distance. So in other words, if I wanted to plug in, if I took this equation here and plugged in x equals 0, y equals 0, crushed out the calculation, what would that measure? It would be a d, a distance value. But if I plug in x equals 0 and y equals 0, let's see what it actually does give me. Not really part of the big problem, just making sure you're aware of what this function, the power of this function we just made. You suck. At x equals 0, y equals 0, d equals, it's going to be the square root of, so big old radical, 1 plus 4 plus, both x and y go to 0, so that turns out to be 9 squared, 81. So you get the square root of 94. No, lie. You get the square root of 86. I told you I suck at arithmetic. 5 and 1 is usually 6. Okay, you get the square root of 86. What does that square root of 86 mean?
It's the distance from that point on the plane.
Okay, what point on the plane are we actually using?
X0,
0, 0, the origin.
Well, the origin is not a point on the plane.
So is that at any z point?
It's one z point.
That's your z-intercept.
Your z-intercept, yes. If you're using this value of x and this value of y, the only point on the plane that produces is 0, 0, z equals 12. So someone said z equals 12. I really wanted to make sure you're aware that was really just the z-intercept. I think someone said that. Chris, you said that? Somebody
Yeah,
said
I
z
said
equals
that
12.
earlier.
You said that? So, sorry, I may have not heard it or may have misinterpreted it. But it actually is measuring the point from this, our fixed location in space, the 1, negative 2, 3 coordinate, to this point right here. So if we actually did the proper distance formula from here to here, you get the square root of 86 as the distance, okay? Now, here's the thing. We've left this in terms of dummy variable x and y. So of all the x, y coordinates in the domain here, we're looking for the one coordinate that produces the smallest distance right there. Now, the only reason I've got that little right angle symbol drawn is that's what's going to have to be true of the shortest distance. It's not really part of the problem, but what do we want to do now that we've constructed a function that measures distance from that fixed location to any point on the surface? See, if I plugged in x equals 4, y equals 0, z equals 0, I'm measuring the distance to that point, okay? But I want to find the one point that has the shortest distance. What should we do now with our two variable function? In order to find out where this thing has a minimum,
Partial derivatives, then find, well, partial derivatives, isn't it the whole thing or is it just a?
partial, now, if you remember from Calculus 1, there's something you did on these, if you did these problems in Calculus 1. Whenever you're looking for a minimum distance, the distance formula always has this big square root on it. Let me ask you this. If the square root value, if the distance itself is already minimum, would the squared value of the distance also be a minimum? In other words, if this shortest distance here, let's say just for convenience it's 2, is the proper distance. The square of that distance is 4. Is the squared distance from here to any other point on that plane going to be any smaller than 4?
No, because they're all going to be larger.
No, because any other distance is going to be a bigger value, a bigger positive value, and when you square that larger distance, it's going to be a larger squared value. So the distance from here to here is properly root 86. So the squared value would be 86. The only thing I'm prompting you for here is, because we want to do calculus to this, we want to find this thing's critical points and then do its d-test to see if we actually have a minimum at a certain xy location. So instead of doing the calculus to the big square root distance function, what you usually do is you square the distance function just for the convenience of getting rid of the radical and not having to do a square root chain rule in your partial derivatives. So the usual addendum to a problem like this is you want to find the minimum squared distance. All because it offers you this convenience. Jared, I did see your hand up.
You answered it.
Oh, okay. It's twice tonight. I'm good. I'm on a roll.
So if you want the actual distance, you can find the points later on and then do the calculation later.
Yeah. I mean, if any distance from that point to the point of the plane, all you need to do is plug in the XY coordinate that you know from the plane, and this guarantees to lock in the Z coordinate from the plane because you've used the plane's equation to get that Z value. However, let's probably take some liberties and simplify some of this. I may leave those two in binomial squared form without foiling them, just because, I mean, the calculus won't be too bad with them. I mean, your partial with x, that gets differentiated, that completely wipes out. So maybe leaving them in that squared form will be okay. This one, let's see. It might lead to a hot mess, but I'm going to take my chances.
I already foiled that one too.
I'm going to take my chances on leaving it in that form. Collect the 12 and the negative 3 together, so it's a trinomial squared. So to avoid any more algebra than I have to, let me see if I can take my chances with leaving that as is.
Would it be safe basically calling this d squared?
Yeah, notice all I did was I changed from lowercase d to capital D. I know. If you want to call it d squared, I'm worried about you putting a square there and thinking you have to do some kind of implicit derivative or something like that. So maybe just call it capital D. And we'll say capital D represents the squared version of the distance function. And I'm going to let you know, some of you already know this, but on the back page of these notes, I kind of put my own set of problems. Any problem where you're finding the closest point or a minimum distance, you're going to want to use that squared version of the distance formula, okay, as opposed to the radical version. Just because with the radical there, the chain rule can be potentially messy. And if the squared distance is a minimum, you're guaranteed that the regular distance is also going to be a minimum. Okay? So you'll use this same kind of tactic on number 7 and 8. And again, this is optional. You don't have to do this. I mean, you can stick to the textbook homework. But FYI, I wrote these problems, and I'm writing your tests. So take that for what it's worth. All right? I will post the solutions to this so you can have, you want to see the solution, make sure you got the problems right. So I'll make sure that those are put on D2L as well. So let's take our chances on leaving this in this form, and now get our CPs. Well, I'll put S in parentheses because I think we should only get one. I mean, if you think about the geometry, there can only be one minimum point, so there should be only one critical point in this calculation, hopefully. So let's see, D's partial with respect to X, and capital D's partial with respect to Y. I want to set those both equal to 0. So leaving them in this form, the partial with X makes this go to 2 times the quantity X minus 1 to the first power, and the chain rule multiplies by a 1, so that's really all you need from that first term. The y plus 2 squared wipes out because it's only a function of y and constants. And then this trinomial squared becomes plus 2, 9 minus 3x minus 4y, bless you, to the first power. This one does need a chain rule because your inner function of x is negative 3x, so you have to multiply the outside by negative 3. But that's my complete first partial with respect to x. I'm going to force that to equal 0, and we'll see. Well, actually, do you see what happens? What kind of equation is that going to turn into? Starts with an L and rhymes with linear.
Oh, there.
It's linear. Every x uses first power, every y uses first power, so we may actually get away with solving a system of linear equations where you can use simult or a 2x3 matrix, in reduced row echelon form, if you know what I'm talking about. If you don't, that's coming up later. Not in this class, but in another class. Your partial with respect to y, so it looks similar. This first binomial squared wipes out. This becomes 2 times y plus 2 to the first power. Don't mistake those for primes. Those are just my poor attempts at 1 exponents. And then this one becomes plus 2 brought to the front, inside left alone, decrease the power to 1, and the inner function of y would produce an outer derivative with the chain rule negative 4. So let's see. Let me do some marginal algebra here. This first equation, the coefficient of x will be 2x minus 6x is negative 4x. Please call me on a mistake because I'm only human. I do make mistakes. My coefficient of y here will be, I did make a mistake. Pooh. But I caught it, so it doesn't count. I forgot this guy right here. This is technically negative 6x times negative 3, so it's really positive 18x with 2x, 20x. That's Bob. Okay. So scratch that. So watch out for that chain rule multiplier. Maybe I should have went ahead and turned this into a -6 in the front. My coefficient of y only comes from here. So -6 times -4y is positive 24y. My constant term comes from a few things. A -2 here, along with -6 times positive 9, that's usually -54. So -54 with -2 is -56. So that equal to 0. So that's just the sort of simplified version of the first equation. Let me try it with the second one too. Coefficient of x is going to be -4 times 2, so -8 times -3, 24x. The coefficient of y from here is going to be -8 times -4 is positive 32. Positive 32 with 2y is plus 34y. Okay? The constant term is going to be -8 times 9, so -72. -72 plus 4, -68 equals 0. So it's a linear system. How many of you, have the simul program on your calculator?
What, is that on this?
Yeah, 83 or 84. I've got one that'll work with 84 or 83s. It comes up rarely here. I mean, this is nice. I mean, what you can do is, first off, make that first equation simpler. If you bring the 56 over, you can divide both sides by, what, a 4 or something, and make the coefficients a little bit neater. So if I take that liberty and do that, if I divide both sides by 4, that becomes 5x plus 6y. If I take the 56 over here and make it positive 56, 56 divided by 4 is usually 14. Okay, same thing with the second equation. Bring the 68 over. Everything here, unfortunately, only has a 2 in common because that's 34. It's not a multiple of 4. So if I cut this equation in half, that becomes 12x plus 17y equals 68 in half is 34. Because on the right-hand side, it'll be positive 68, and then cut it in half there. So when you have a system like this, I mean, usually what you could do algebraically is do an elimination. Like multiply the top equation here by -12, multiply the second equation by positive 5. That gives you -60, and positive 60 is your x coefficients, and then you can eliminate x. But if you got the simul program, go in and use it if you can. My link cable's in the car, so when class is over, I'll run and grab it, and we can trade Pokemon if you want to. So the way the simul program works is, programs. Simul is, there we go. When you pull up a program, it prompts you for how many equations you want to solve. This is a 2-equation system, so you just type in the number of equations first. And the program prompts you for the x, y, and constant coefficients in order from left to right. So you only need to type in the 5 and the 6 and the 14, okay? Anybody learned that you had this already and didn't realize you had it or something? Maybe not, okay. So I need to type in the A value here they're prompting for is 5, the B value they're prompting for is 6, and the C value is 14. So A equals 5, B equals 6, the C, the constant value is 14. And that completely enters, yeah, you could do a 2x3 matrix also.
Okay, good.
Yeah.
That's what,
This represents the rows of the 2x3 matrix, and then what you want to do is ref that matrix, reduce row echelon form, and that'll give you the
reduce row
solutions.
echelon form. Is that
Reduce
what
row
that's
echelon
one
form,
thing?
yeah. And then you type in the coefficients from equation 2, left to right, those are 12, 17, and 34. The one thing that sucks about this program, and it really does suck, is if you type in one of the coefficients and you hit enter and lock it in, you've got to start all the way over. There's no way to back step and say, oh, I meant for B to equal -17 or something like that. You've got to scratch it and start all the way over. So when you hit enter after entering the coefficients for equation 2, it gives you the solutions. So, and this represents, technically we only get one solution. Geometrically that should make sense. Because of all the points on this plane, how many points can be closest or minimum distance to that fixed point in space? 1. So there was no hope of getting anything but one critical point. So I'm tempted to skip the D test, but I'd be a really crappy Calc3 teacher if I didn't. So you got a critical point. It's not the prettiest point in the world, but it's a point.
Okay.
And that has to be the XY coordinates of a point you plug into that plane and give you the Z coordinate later. So this solves to give us a CP of 34/13 for X and 2/13 for Y. Okay? So it's only one critical point, so not too bad of an application of the D test. So our D value here, oh crap, overlap notation, poo. This I mean to be D test D, not
Yeah.
our function D. So let's just say D test equals second partial with respect to X. Now notice, assuming what I simplified there to be correct, what is the second partial with respect to X? 20. Yeah. I mean, here if you go bit by bit, you have a 2 and then a -3 times -6. So you have 2 plus 18, you get 20 that way. But that's the handy thing about already simplifying this is the variables are still in the same position they would be in this first partial with respect to X. So 20 is your first X partial, your second X partial. So notice that it's positive. Your second partial with respect to Y, you can get from this Y coefficient here, positive 34. Your mixed partial is going to be what? This is fxx, so that partial with x. This is fyy, that second partial with y. So this is the fxy. So it should, you want to start with the first partial with respect to x, and then take its partial with respect to y, so it should be 24. And notice, if you did y's partial with respect to x, you still get a 24. So either way, you're going to get 24 for that second mixed partial. You should, because they should always be the same. And that gets squared. So according to this, 20 times 34 is bigger than 24 squared. That should be a positive number. And dxx is positive 20. So with a positive value of d and a positive value of your second x partial, what's your conclusion about this? Minimum. You're at the bottom of concave up on whatever this distance graph function looks like. Keep in mind, we're not talking about the graph of the plane, we're talking about the function that we're analyzing, the distance function, the square distance function. So, those both being partial means min distance occurs at that critical point, that xy coordinate value. 34/13 for x, comma, 2/13 for y. Now technically, if you answer the question correctly, at the top of the page, it says, what is the shortest distance from that fixed point to the plane? Have we really answered the question yet?
No.
No. What we actually have to commit to now,
Is we have to plug those into our.
into our original function.
Mhm.
The original function being the distance function right here. So, the cool thing about this program, I think, if I'm not mistaken, is since it actually stores the values of x and y as the letter x, well, you convert it to a fraction. Yeah, and the letter alpha y. So you can actually use what's stored as the letter x and y and just type in this calculation here using the x and y values that are already stored there. So the minimum distance, if I plug in these values of x and y into this function, that'll be parentheses, and keep in mind, if we're using this function, remember that's the square of the distance. We'll want to take the square root of that when we're done. So if I plug it into here, it's the square root of x minus 1 squared plus y plus 2 quantity squared. Oh, hello. Alpha y plus 2 quantity squared. And again, it's using those stored values that it already has for x and y. That's the cool thing about this calculator. One of the cool things. And then plus, parentheses around 9 minus 3x minus 4y squared. And am I doing things on this calculator that you've never done before?
With the x, y. I never-
Yeah, you've got, if you didn't have them stored in from the program already, have you ever used the stow button down here?
Yeah.
It's a storing feature, but it says stow, so I call it the stow button. Stow is what it says.
So how do you?
It allows you to store values as variables. Pardon?
I was going to ask how you actually move from x to t to theta.
Oh, that's This is the button that you usually use in your graphing mode. When you go to y equals, the y equals screen, and you graph a function, to pull up x as a function of x, you usually hit this button. There's three other things you can graph in this calculator. You can graph parametric curves that use the variable t. So you can do two-dimensional parametric curves like the things you did in chapter 13 with the r functions and the velocity and the acceleration. Theta graphs polar curves where r is a function of theta. N is a sequence. Some of you may have done graphing of sequences in calculus 2 at the end of the semester. So there's 4 different kinds of independent variables you can have. X for a function, t for parametrics, theta for polar, and n for a sequence. But yeah, in function mode, it defaults to being x.
Okay.
And it's the same as the variable x that you use. So doing this whole thing with the x here does not hurt the graphing ability of your calculator in any way, shape, or form. X is probably the most frequently changing variable on your calculator, so it's just versatile to use it. So the squared distance, if I plug in these values, and if I'm anticipating a rational number, the squared distance is 98 over 13, which means the actual distance itself would be the square root of 98/13. So that raised to the 0.5, that's about 2.75-ish distance units to go from that fixed point in space to that point of the plane.
That was awesome.
Is it
Do you feel
normal?
smarter?
Yes, it was good.
Who's intimidated by this?
Is it normal too?
Is it normal to be intimidated?
Normal?
Is it normal that, yeah, if you actually constructed a vector from that fixed point in space to that point that we found here, now keep in mind though, this is a 3-dimensional coordinate, so what's really missing from the point on the plane? The z coordinate. So that means you have to go way at the top of the problem where it's 3x plus 4y plus z equals 12 to find the z coordinate on the plane. So if you use that fixed point as the tail and that 3-dimensional coordinate is the head, the magnitude of that vector would be that long. And that vector would be parallel to the normal vector to the plane surface. Oh, hey, yeah. And what is the normal vector to this plane surface? Tying it in with something you've done before. Let me zoom out so you can get the answer. What is a normal vector to this plane surface?
3, 4, 1.
3i plus 4j plus 1k. Because remember, the coefficients represent a normal vector. So if you did make a vector out of that, from tail to head, it would have to be some scalar multiple of that 3, 4, 1 vector.
And it would be 2.75 units.
And it would be 2.75-ish units long in magnitude. Okay, you don't seem impressed. You just have this stone-faced sort of look. I'm not saying it's a bad thing, it's just hard for me to read your emotions. So maybe I should stop trying to read your emotions. But you understand what I'm saying. Okay, because you'd probably say otherwise. Okay, good deal. So any problem where you're prompted to find a minimum distance, you're going to have to be given like a fixed point in space, as well as in most cases it's the fixed point and its minimum distance to some kind of surface. So the problems that I've got here on the back page is a similar one. Here it is. What point on this plane is closest to that one? So in this case, you're not really trying to find the minimum distance. You're trying to find the point on the plane surface that's closest to this. So it's the same rudiments. It's the same problem. But your answer is really trying to find a point on the plane that produces that minimum distance, okay? So in other words, you don't have to do this step right here at the end. You just want to find out the x, y coordinates and then find the z coordinate that comes from the plane to it. The only variation on this theme is in problem 8, you're doing the same idea, but in this case you want to find the point on anybody know what that surface is? It is a cone, yes sir. What point on this cone is closest to that fixed point in space? And you can take for granted, in each case, these points do not lie on these surfaces. If I plug in 4 and 2 for x and y, I do not get 0 back for z. So that's definitely a point that's not on the plane. So there is a proper solution to each of these. Can you think of how many number of solutions you could get? If you're looking for the minimum distance from a point in space to a plane that doesn't contain that point, how many solutions should you get? 1. There can just pretty much idealized right here. 1 point fixed in space, there can only be 1 minimum distance to a plane. But you call this a cone, but do you remember what it looks like when you graph it properly? I mean, it's got the apex of the cone at the origin.
Hourglass kind of shape?
Yeah, and most people think it's just the part that opens up. If you solve this as z equals root x squared plus y squared is the upper half of the cone. But with z being squared in this implicit form, it's both the hourglass shape. It's the upper cone and the bottom cone. And so this point, where does this point lie in space? With a z coordinate of 0.
On the XY plane.
Lies on the xy plane. So you've got the xy plane here, the origin in the middle, cone opening up and down from the origin, and then this point over here on the xy plane. How many points on this implicit surface are closest to that one? There should be 2 because of the symmetry. So really you should get 2 points here. And what's special about those 2 points?
They're opposite.
Well, they'd have to be symmetric about the xy plane. So they probably have the same xy coordinate, but this may use z equals 1, this may use z equals -1. It's the only thing that would vary. Okay? So you should get 2 solutions here if you think about the geometry behind it. Yeah.
Could you potentially be closest to the converging point of 2 cones and only have one?
That's what I was just wondering, because
Could
if
you-
it's 4-2,
Oh, okay,
then
yeah.
you'd be closest to the positive cone.
If the point you're localizing here, or fixing in space, were not symmetric, right there where the apex is on the xy plane, if this point were given a z coordinate of maybe 3, then it would only have, that's not what you're asking though.
No, it's on the
three
z
space.
plane. Could it be closest to the convergence point of the 2 cones, basically 0, 0, 0?
So could that be, the only time that would be the closest point
If
is,
it's a really skinny tapered cone?
no. If the point, see, this is a point that lies kind of on the outside of the
Wouldn't it
cone.
have to lie on one?
What if it lies on the inside of the cone?
Then you'd have 2 points on the.
So it would have to lie on
surface.
two.
What if it was like right in the middle of the circle?
Let's see. If we draw a little cross section of this cone. Okay, so it looks like a big X.
Yeah.
Here's the origin of the XY plane. So we're on the XY plane looking at this kind of laterally. And the point where we're given in the problem is kind of like right here, somewhere on the XY plane. So it seems to me, it seems pretty straightforward that there should be
Okay.
2
Oh, yeah,
symmetric
'cause that's gonna be
Okay.
a hypotenuse, it's gonna be longer than.
So then, because those would have to be congruent distances. If the point were maybe somewhere askew and not symmetric, like right here, somewhere above or below the XY plane, I think in that case you'd only get 1 solution, because this would have to be a greater distance. Any other connection from here to the bottom half of the cone would be a bigger distance than that dotted one.
Your first drawing answered my question.
Oh, okay, okay.
Yep.
Let me show you another one. Because there's also all sorts of other optimization problems that you can do with this d-test information. I've got one more example I want to show you. These are kind of fun, because these come with a pretty cool picture too. You're looking to construct a rectangular box. And the stipulation is, oh, yes, sir, I'm sorry.
I'm sorry, can I get one of those pictures from you?
No. No, and they're such an ass. They're posted on D2L.
Oh, so
If you go to D2L between today and Thursday, you'll see a link that says blank lecture notes used in class, and it says optional. You don't have to bring them to class, but it just makes note taking a lot easier, because I have the proper worded diagrams here, and we just fill in the blanks with the work. You know. So between now, yeah, there's a handful of other. Though you're not the only one who missed out on them. So, but they're posted on our D2L page. So we're trying to create a rectangular box, and the stipulation is the box only exists in the first octant, so that's just a convenient image. We only need to see the first octant image here. One corner of the box is located at the origin, and the opposite, I guess I should say opposite diagonal corner of the box is some point on the graph of another kind of tetrahedron plane like this. So you're using the equation of the plane 2x, so this would have x-intercept of 6, a y-intercept of 3, and a z-intercept of 12. It's not the same plane, but it has the same z-intercept, but it's not the same as this one. So one corner is at the origin, and the opposite diagonal corner is some point that's on this surface, this tilted plane surface right here. So then there's an infinite number of first octant points on that plane. So think about all the extremes of the size of this rectangle you could get. If you take this opposite diagonal corner here and move it closer to there, what's your box going to look like?
Really long and skinny.
Long and skinny with a relatively small height. Okay, so that would have one particular volume to it. But animating this point, through all the possible points on this plane, there's probably just one location, maybe 2 locations, where the volume of that box is as big as it can possibly be. Okay, so what we want to do is determine the x, y, z dimensions, determine the 3 dimensions that this box needs to have to make it as big as possible. So there's your superlative. largest possible box, meaning maximize the volume. Previously, it was the shortest distance, so you wanted to minimize a distance function. So in this case, we want to come up with largest such box means to maximize the volume. Now, there's a convenience about having this box with one corner at the origin and the opposite corner being some point on that plane. Okay? How do you find the volume of any box? Rectangular solid. Yeah, length times width times height. Okay? So if one corner is at the origin, in order for me to get to that point on the opposite diagonal, I'd have to go some x distance this way, some y distance that way, and then some z distance up. But what is special about the x and the y and the z distance that you travel? Where do you end up? You have to end up at a point
2, 4, 1.
Well, not necessarily 2, 4, 1. You have to end up at a point, some generic point on the function, the surface, the plane. Yeah. So going this distance for x, that distance for y, and that distance for z locates a point that's on that equation. Okay? So once again, if we generically represent the length or the width as x, so call this my x, generically call this my y, the z value here has to come from z equals what?
12 minus 2x.
Yeah. If I'm just saying any x and y value, that I plug in here, the z value has to depend on the x and y based on this equation. So I'm just saying x is generic, y is generic because they're my independent variables. I can independently choose x, but z is fixed. If you let z be the dependent one, then the z dimension of this box has to come from z equals 12 minus 2x minus 4y. Okay? True. Is that too big of a leap of faith for you? Because I hear some affirmative answers out there, but then I also hear crickets. Any questions or any what ifs or? I want to try to get as most out of our contact hour as possible, but let me just keep on working. Maybe it's sinking in pretty well. So I want to maximize the volume of this box. The other handy thing about it being cornered at the origin is the same generic x can play the role of width. The generic label y here can play the role of length, and the generic z, well, not generic, it's a specific z, but the value z can play the role of height. So the volume in 3 dimensions for this particular box is just x times y times z. That's a convenience of it being cornered at the origin. Since it is cornered at the origin, starting from 0, you have to go that same x distance is the same x dimension as your box for width. That same y distance leaving the origin, or technically leaving the x-axis, is your length dimension for the box, and then going up that z-coordinate is your height dimension for the box. So that's one of the conveniences about it having a corner at the origin. If the corner was some other point, you'd have to sort of do a distance calculation. Like if you were leaving a non-0, 0, 0 coordinate, something like, x equals 1, y equals 4, you'd have to say, well, x minus 1 is the horizontal distance, and then y minus 4 is the horizontal length or something, and then z minus something is your height. So the convenience of it being cornered at the origin is you can use the same x, y, and z in this picture as the dimensions length, width, and height. But I can only do d-tests on a function of 2 variables. Currently, this volume is a function of 3 variables. So, replace your z with what has to be true for any z coordinate on that plane, and that turns our volume function into a function of x and y, which would still